So this is still the calculation of the basic reproductive number, but this is part 2. So the last thing we discussed was this definition of the operators F and V, and we were precisely and rewriting the model into compartments that have disease. The X variable denotes disease compartments, and the other compartments are stored here with the Y variable. And we were making the analogy connecting this form into the model for birth and death processes. Okay, so here is where we start throwing some of these technical um, things, assumptions for the existence of an equilibrium that now in this form where X denotes the disease compartments and Y denotes the non-disease. When X equals 0 means that there is no way of having the epidemic settling or having disease in the population. Okay, so this equilibrium is denoting that there is a lack of disease, which is precisely what is denoted here with X equals 0. The first component now is we have decomposed the state variable into X comma Y, X being the disease compartments. When they are 0 is what we call disease free. And so we are setting some assumptions as to basically defining precisely what is the meaning of having this equilibrium with relation to the operators F and V. So when X equals 0, F vanishes and V also vanishes. We also assume that F as an operator, even though is valued at an input that is in an input that has as many entries as n plus m, the output here of every component is assumed to be a non-negative real number. Okay, and when we say non-negative x, we mean that that's happening component-wise, or every entry of x and every entry of y is a non-negative real number. This function or operator represents new infections, and these new infections are like the new arrivals. They are not assumed to be negative numbers. The other technical consideration here is whenever there is a lack of um, disease individuals, whenever x, y is 0, then we assume that v is either negative or 0. So each component, v sub I, is representing a net outflow from the compartment I and must be negative whenever the compartment is empty. These are just technical considerations to make sure that this model is in this form is well posed. Then we have another constraint about making sure that that net outflow, when added up over all possible components, we make sure that this is adding up to a non-negative number, and this sum represents the total outflow from all infected compartments. Okay. Um, then we have another note here, terms in the model leading to increases in the total sum of the disease compartments are assumed to represent secondary infections, and they therefore belong to the operator F. We assume that the disease-free system takes this form. Okay, here prime is denoting derivative with respect to time, and that this has a unique equilibrium that is asymptotically stable. This means, in other words, that solutions of this form approach a point that is 0. Y naught here is supposed to be a constant, right? So it's this convergence. It's not necessarily initial conditions, but it's more like some type of constant vector. And this convergence happens as t goes to infinity. It's the whole notion of having a stable equilibrium, an equilibrium that satisfies that there is no infection in the population. Okay, this disease-free equilibrium is what we will denote here with DFE. Now, how do we compute R naught? And this is where this will become even more interesting. this calculation of R naught is going to rely on a few assumptions. So first, we compute the disease-free equilibrium. Second, we'd like to check this. See these expressions here. First, we'd like to check the partial derivative of the operators. Okay, we're going to have to inevitably make sure those partial derivatives are computed. Um, so we can see that when we evaluate this partial derivative of f with respect to y, remember y are the variables for non-disease compartments, that partial derivative evaluated disease-free is vanishing, is equal to 0, and so is the partial derivative of v with respect to the non-disease variables. Also evaluated disease-free, then they become 0. So because of that, then, and this is the strength of these type of methods, then we are able to only operate or concentrate our attention into just one subsection of the mole, which here is denoted, again, prime is denoting derivatives. So we're interested now on the submole, which is decoupled from the remaining equations, meaning that now we're only operating with the equations, the compartments, the state variables that correspond to the disease compartments. Okay, and now these equations are some of what's going on here is that there is a linearization of the original system, well, the linearization of the reformulated system around this equilibrium called the disease-free equilibrium, and when we have that linearization, this becomes a linear system. This matrix F here is a matrix, so is V. Notice that this is F different from the fancy F we had before. That fancy F is an operator F. This F is now going to be a matrix, and so will be V. These matrices, we're subtracting them, they have to match, their dimensions have to match. So F, their square matrices, they have n rows and columns, where n is the number of disease compartments. And the entries of these matrices are computed almost in the way you would compute Jacobians. In fact, you should think of these matrices as Jacobians. Jacobians are those operators that involve derivatives, partial derivatives with respect to all your state variables, right? So F, the matrix F, is a matrix that looks like this, right? This operator F has n components, and so you take every component and differentiate every component with respect to every single state variable for disease compartment, right? So you have n of those, so that's what happens in the first row, second row, all the way through the nth row, and that's how you compute the matrix F, and you compute the matrix V in a very similar way, because you will be computing partial derivatives of the operator V with respect to each state variable, but the disease compartments, the state variables that now define the disease compartments. So importantly is that now we're basically only working with the disease compartments, with the linear system describing the dynamics of disease compartments. We rely on these two matrices F and V, and what we do next is that we use those matrices to form yet another matrix called the next generation matrix we had discussed in the past. Okay, next generation matrix. And so the way we form this next generation matrix is multiplying. First we have to compute the inverse of V, and then we multiply F by on the left side of V inverse. Said another way, we multiply F times V inverse. For those of you that are right now having flashbacks to your juicy numerical linear algebra and your even juicier linear algebra back to the good old days, then you will remember and you will know that these matrix operations are, well, there's no free lunch, right? They're not necessarily, they are involved, okay? There are methods for computing. Once you compute V, you define what V is, okay? There are methods for computing the inverse of a matrix. So you just keep that in mind. But once you figure what is the inverse of that matrix, you multiply F times V inverse, and that is the matrix K, known as the next generation matrix. The ij entry, the ith jth entry of K is the expected number of secondary infections in compartment I produced by individuals that were initially in compartment J. Okay, R0, R0, the basic reproductive number, is the spectral radius of the next generation matrix. Okay, and the spectral radius is denoted as rho of k, and we're referring to the eigenvalue that is the largest in modulus. Okay, out of all the eigenvalues of the next generation matrix, then the spectral radius is going to be that one that has the largest or maximum value of modulus. Okay, so what we really want to do to calculate R0 is to compute the eigenvalues of this matrix and determine which is the one that has the largest spectral radius. So we will work an example that illustrates these steps, and that's what we'll do next.